Okay, Bismillahirrahmanirrahim. Today we're going to start with a new topic, which is topic 15. This is under the organic chemistry, and this is another functional group that we are going to look at. They're called halogenoalkanes, or sometimes called haloalkanes. For those of you without the printed notes yet, you can just copy things down first, or if you don't have enough time copying, later on you can rewatch the YouTube video. Okay, right. Halogenoalkanes, or sometimes called haloalkanes, or they're called alkyl halides. Okay, so halogens are your group 17 elements, your fluorine, chlorine, bromine, iodine. So basically it is an alkane. They come from an alkanes. It's just that one or more of the hydrogen atoms have been replaced with a halogen atom. Okay, so in a halogenoalkanes, you can have one or more halogens. In terms of naming, usually halogenoalkanes, they are named as prefix. So the halogens come before the principal chain. Okay, for example, if you have hold on. How do I pause this? Hold on, yeah, I need to get this call first. Okay, sorry about that. Resume share, no. Wait. Oh, so it was recorded just now. Okay, never mind. Right. Okay, back to naming. Everyone okay? Can hear me? Please just say something in the chat so that I know that I'm talking to someone. Okay, thank you. Right. So back to naming. As we all know, they are named, the halogens are named as prefix, which means that they come before the name of the principal chain. So here we have an example of a 1-bromopropane. The number 1 is for the position of the bromine, and propane is the principal chain. So principal chain is always the longest chain, and then you just give the smallest position to the halogen. Okay, so there are actually two possible ways of numbering the carbon. You can start with number 1 from the left, or you can start with number 1 from the right. Okay, for the compound molecule on the right, again, we look at the longest principal chain. So that's 4 carbon. So that's why you've got the principal chain named as butane. Anything hanging off the principal chain, you have to give the number of the side chain. Okay, so if I highlight the principal chain, again, this is nothing new for you. Cl is a chloro, and CH3 is a methyl, and they are positioned at carbon number 2, hence the name 2-chloro-2-methylbutane. So you may ask me which one comes first, the chloro or the methyl? It follows the alphabetical. C comes before M. Okay, whereas butane is just the name of the principal chain. right? Okay, moving on to our first learning objective, which is to classify halogenoalkanes into primary, secondary, and tertiary. Okay, Apple has just joined us, right? So classifying your halogenoalkanes in terms of primary, secondary, and tertiary in the same way you have classified carbocation. In the previous topic, I have introduced to you the idea of primary, secondary, and tertiary carbocation. So for halogenoalkanes, we have the same system, okay? But here you want to look at where your halogen is, so that's your bromine, and so you look at that carbon, okay? So the one that's highlighted in yellow. So you want to count the number of alkyl groups attached to the highlighted carbon, okay? Alkyl groups directly attached to the highlighted carbon because that carbon is where your halogen is sitting on. So if we count the number, it has to be the direct bonds, okay? So on this highlighted carbon, there's one hydrogen, second hydrogen, and this is your alkyl group, and it's called the ethyl group, okay? I don't know if you can spot that, but C2H5 is an ethyl group, and it falls under, and it is an alkyl group, okay? So you only have one alkyl group, therefore we call it a primary halogenoalkane, okay? I guess you can see the trends from here. Again, you want to highlight where your halogen is, so that's your bromine, and therefore we are interested in that carbon that is directly attached to the bromine. Again, for the same method, you look at the bonds that are directly bonded to that highlighted carbon and count the number of alkyl groups attached to it. Okay, so this is a methyl, 1. This is another methyl, 2. So that is a secondary halogenoalkane. For obvious reason that it's called secondary is because there are 2 alkyl groups attached to the carbon with the halogen. Okay, so I'll just label this as methyl, as we all know, CH3, and this is also a methyl. Lastly, tertiary halogenoalkanes are for when 3 alkyls are directly attached to the carbon halogen bond. Okay, so a carbon halogen bond is this carbon chlorine. So that's your carbon halogen bond. And so you want to look at the 3 other bonds the highlighted carbon is attached to. Okay, so you can see that this is a methyl group. This is also another methyl group, which is an alkyl, and that is an ethyl group. So that there are 3 alkyl groups or 3 carbons attached to the carbon atom adjoining the halogen. Okay, sometimes you will see in textbooks or on the internet, a carbon halogen bond is represented as the CX bond, where X can be fluorine, chlorine, bromine, or iodine. Okay, so that's how you identify your primary, secondary, and tertiary halogenoalkanes. In the same way, you would identify a primary, secondary, and tertiary carbocation. So just to remind you, a carbocation is the intermediate in an electrophilic substitution reaction of alkenes, which you have seen in the previous topic. Okay, so here is a general overview of how to identify a primary, secondary, and tertiary halogenoalkanes. Okay, so that carbon halogen, carbon hal, Hal, that's actually your halogen, but usually in most textbook, they will just represent it as CX bond. Okay, what I want to show you is the fact that R here represents an alkyl group. Okay, so 1 alkyl group, primary, 2 alkyl group, secondary, and 3 alkyl group is tertiary. So R, R1, R2, R3, these are representations of your alkyl group. Okay, so R is not a new element or a new symbol. It's the same symbol that I have introduced to you in the previous topics. It is the representation of an alkyl group. What's an alkyl group? A group that has carbon and hydrogens, right? It's actually, it comes from your alkane, but with one hydrogen less. So that's what we call alkyl. Okay, looking at the physical properties of halogenoalkanes. First, we want to look at the bond polarity. Okay, so carbon halogen bonds, CX bond, so you can see that, are polar because the halogens are more electronegative than carbon. So first example that I'm going to use is carbon fluorine bond. We know that fluorine is the most electronegative element among all the elements. Okay, in the periodic table, fluorine has the highest electronegativity value. What it means is that the bonding electrons that are supposed to be shared in the middle between carbon and fluorine is pulled closer to the fluorine. Okay, sorry, I should only be drawing 2 drops, 2 dots. 2 dots to show that it is a bonding electrons. Okay, so because fluorine has a high electronegativity, automatically fluorine will become delta minus and carbon will become delta plus. Okay, this works for carbon chlorine as well and carbon bromine. Carbon iodine is almost nonpolar because it just means that the electronegativity of carbon is almost similar to the electronegativity of iodine. Okay, same thing in carbon chlorine bond. Chlorine will be delta minus, carbon will be delta plus, bromine will be delta minus, carbon will be delta plus. Okay, but if you compare carbon fluorine and carbon bromine, okay, we leave carbon iodine out of this because we say that it is almost nonpolar. Okay, the polarity or the most polar bond is the carbon fluorine. Polarity is usually based on the difference in electronegativity, okay, not the sum of the electronegativity value. So this is a common mistake made by students thinking, oh, carbon is 3.1 and bromine is something. Okay, so the most the most polar bond is the one that has the biggest difference. You have to subtract, take the electronegativity value of fluorine minus the electronegativity of carbon. Okay, right. Going back here. So we know that in a halogenoalkanes that the carbon halogen bonds or the CX bonds are polar, whereas the rest of the molecule, the carbon-carbon, carbon-hydrogens, carbon-hydrogen bonds, they are nonpolar. Okay, because they don't have big difference in electronegativity. Next, boiling point depends on the strength of the intermolecular forces. Of course, this is the same as other functional groups as well, alkanes, alkenes. In the case of halogenoalkanes, however, there are 2 types of intermolecular forces. But of course, if you have never mind. Yeah, two types. Okay. So the first one is the ID force, which I believe in your notes is written as the van der Waals forces. So can you please change, instead of calling it van der Waals forces, which is not wrong, but it's not something that we use in our syllabus. Okay. So can you please change that? Instead of van der Waals forces, change it to ID force. Okay. And of course, because there is a polar bond in your halogenoalkanes, there is an additional intermolecular forces, okay, which is your permanent dipole. What factors affect the strength of the intermolecular forces, which in turn will affect your boiling point? You have to look at the factors that affect ID force and the factors that affect the permanent dipoles, respectively. Okay, I think all of you know, we've been talking about this from time to time. For ID force, the first factor is the number of electrons.
The
Yes,
second is surface area of contact.
correct. Thank you. Surface area of contact. Okay. And then for permanent dipoles, usually the idea is the more polar bond, the stronger the IMF. Okay, so in the case of CF versus CBr, CF is more polar, therefore you would expect the permanent dipole will be strongest in molecules that contains carbon-fluorine bond. Okay, right. Next, solubility. Again, the same idea. The idea is polar dissolves in polar. Polar loves polar, and non-polar loves non-polar. Okay, but it's a bit tricky, because if you think about the halogenoalkane, just a simple one, say fluoro propane, okay, where everything else is just carbon hydrogen bond. And then of course, always draw the dipoles. Okay, so for this molecule, the carbon fluorine part, or the carbon fluorine bond of the molecule, is polar, whereas everything else, carbon hydrogen, is non-polar. Okay, so it's actually a bit of both, right? It depends on the molecule. If you have a lot of carbon fluorine bonds in the molecule, it will be dominant polar. If you have longer hydrocarbon tails, usually we call it the hydrocarbon tails, then your molecule overall becomes non-polar. So there is no definite rule that says halogenoalkanes are soluble in polar solvents or soluble in non-polar solvents. Okay, but generally they can be soluble in water, especially around this polar head, carbon fluorine head. Okay, whereas for the hydrocarbon tails, because you know that this region are non-polar bonds, therefore they become non-polar, they will only dissolve in non-polar solvents. Okay, so organic solvent, if you see here, soluble in organic solvents are usually non-polar, or a mixture of polar and non-polar. Okay, so it all depends on the structure. Okay, moving on. So that's the physical properties of halogenoalkanes. Now we move on to the chemical properties. Okay, chemical properties are things like how they behave in a chemical reaction. Do they react fast? Do they react slow? Do they react vigorously or gently? Okay, so these are all the chemical aspects of halogenoalkanes. Okay, so the next learning objective, we want to look at the different reactivities of halogenoalkane. So using the reaction of halogenoalkanes with silver nitrates. Okay, so there's a lot of things in this learning objectives, but we'll just I break it down into different things first. Okay, so before we look at the reactivity of any molecules, okay, we want to look at the bond energy, because in a reaction it involves breaking of bonds in order to form a new bond. So we need to look at the idea of breaking this bond. Is it easy to break the bond, or is it difficult to break the bond? Okay, so bond energy is the measure of the bond strength, which you have come across already. The definition of bond energy is given is the amount of energy needed to break 1 mole of the covalent bond to form atoms in gaseous state. So the definition is not important for this section, but it will be when you do thermodynamics later on. Okay, so what's thermodynamics? That's sorry, it's not thermodynamics, it's chemical energetics. Okay, so that will be covered later on. It's actually topic 5 or topic 6, if I'm not mistaken. Okay, it's under physical chemistry. Right, so the idea is the higher the bond energy, that means the stronger the bond, therefore the more difficult it is to break. I think we all can agree with that. Okay, the stronger the bond, the more difficult it is to break. That means the more energy you require to break that bond. Now, to find the bond energy, you can actually find it from your data booklet. Okay, so I have some data, some numbers for bond energy for the carbon chlorine, carbon bromine, and carbon iodine. Okay, so you can see that the numbers are getting smaller as you go down, going from 340 to 80 to 40. Okay, 340 to 80 to 40. And carbon fluorine, somehow it's not included in the latest data booklet, but I managed to get this number from the older ones. Okay, so you can see that the carbon fluorine bond has the biggest bond energy. That means this is the strongest bond. You need 467 kilojoules of energy to break 1 mole of that bond. Whereas for carbon iodine, you only need 240 kilojoules to break 1 mole of the carbon iodine bond. Okay, so there's an explanation to this. Okay, why is it down the group the bonds get weaker? Okay, so as you go down the group, the halogen gets bigger. Okay, due to the additional shells, so fluorine will only have 2 shells, chlorine 3, bromine 4, iodine 5 shells. Okay, so the halogen gets bigger. Fluorine is the smallest hydrogen, and iodine is the biggest halogen in terms of atomic size. Okay, because as you go down, the number of shells are also increasing. Right, so because of this big size, the bonding electrons get further away from the nucleus. Okay, it becomes more distant from the nucleus. Therefore, it is easier to break them. Why? The attraction is between the positive nucleus and the bonding electrons. Okay, so if I just draw fluorine, okay, and there's an attraction in the middle, for the electrons. So for example, carbon. Okay, so the bonding electrons is here versus iodine 1, 2, 3, 4, 5. So you can imagine, even though my drawing is not great as usual, okay, that's the bonding electron with carbon. So you can see the distance, okay, the nuclear attraction for carbon iodine is bigger than the nuclear attraction for carbon fluorine. So that means the longer the bond, the weaker it is. The shorter the bond, the stronger it is. Okay, so that's what the explanation is trying to tell you. Bigger size, the bonding electrons are further away from the nucleus, therefore the weaker the bond is. Okay, right. Let's see. I'll let you copy that down first. I don't remember what's on my next slide. Okay. Okay, I'll move on. So, halogenoalkanes actually undergo substitution. Well, there are two reactions that they undergo, which is substitution and elimination. Okay, but the most reactions that will be covered will be at the substitution reaction. Okay, so what happens during the substitution is, if I just write down an equation quickly, just for a simple, say, iodine. Okay, we use an iodoethane. Okay, to react with water, for example. Okay, no, hydroxide ions, easier. To form, actually, I will change that color. To form, so what happens is that your iodine, your halogen, not just iodine, your halogen will be replaced with what we call a nucleophile. Okay, so this will be covered in the next topic, where we will look at the not next topic, sorry, next section, where we will look at the attack. Okay, so it's a nucleophilic substitution. So iodine in the halogenoalkanes will be substituted with the hydroxide ions. So I think you can all predict what the product will be. It has now become an alcohol plus iodide ion. Okay, so but what I want to focus is that in order for this reaction to happen, in order for hydroxide to kick iodine out, this bond, this carbon iodine bond, needs to be broken first and foremost. Okay, so how fast, how reactive this reaction is depends on the easiness of breaking the carbon halogen bond. So in this case, it's the carbon iodine bond, but this applies to other halogens as well. Okay, if it's easier to break this bond, that means the reaction happens fast. If it was fluorine, the carbon fluorine bond is very, very strong. So then it will be difficult, or even maybe it wouldn't be able to break that bond. Okay, so the strength of the carbon halogen bond actually determines this reaction, whether it happens or whether it happens fast or whether it happens slow. Okay, so During substitution reactions, the carbon halogen CX bond will be broken. So if you're wondering, this is an example of a substitution reaction. Okay, the CX bond will be broken heterolytically. I'll show you the mechanism and we'll show you how they break heterolytically. Okay, so we know that CI bond will require the least energy because it is the weakest, and the CF bond will require the most energy because it is the strongest. Okay, we have about 6 minutes left. Okay, so the summary is that the weakest bond, in this case, the carbon iodine bond, is the easiest to break and therefore fastest reaction. So we say that iodoalkanes are more reactive than fluoroalkanes in general. Okay, right. So that is all for today. We're going to continue with the mechanism in the next lesson, and then we'll also have a look at this aqueous silver nitrate. But I think I will want to start with I will start with the mechanism first and then revisit this aqueous silver nitrate, because otherwise you will be a little bit lost. Okay. So that's the summary. Your iodoalkanes are more reactive than your fluoroalkanes. And how do we prove this or confirm this? Is by carrying out the reaction of a halogenoalkanes with your silver nitrate. Okay, so I'll just stop there for now. Where's my last slide just now? Okay, so before we go, is there any question? No question?